Let us get into the basics of Makefile now. So, Makefile is again another interesting topic, and because of modern IDEs, since the Makefile process can be skipped, Makefile is quite often misunderstood. But since this is a bare metal embedded systems course, we will learn Makefiles, and whatever compilation we do will be through Makefiles. We will not be using the IDE to create to auto create a Makefile and then generate the binary. We will do it all manually, and thus we will get a good exposure to what Makefile is, how it is written, and the Makefile scripting itself. Now, we saw these commands previously. We have been using these commands quite frequently, that is, compiling the build example main and compiling the core, initialization STM32F411, and then the startup GCC. So we have done this previously, and of course the command to run the linker here. And after all this, we can run the obj copy command to extract the binary from the .out file. So this is in short what we have been doing manually. Though we have not actually used the obj copy command much, but this is the command that is used for creating the output binary file which goes into the flash. Now, Make is a software to automate this process. That is, just running the Makefile contain these commands, and just running the make is going to create a binary and may or may not create the intermediate files, but it will create the map file and the binary at least. And in the beginning of this section, we saw when we saw the flow diagram for the entire build and link process, we saw that the make spans right across that process and automates the whole process. Now, the question might arise as to why we need a specific Makefile for this task. We could automate, we could script these commands in probably a shell script or maybe a Python script and run the same. Why do we need make separately? Now, make has certain advantages over plain scripting. Since make is a build-centered tool, or it's a build-centered software, make not only just automates this process, it also does a lot of dependency checks. So dependency checks, and that it checks for the freshness of the file. That is, if the file has been edited after the last make ran, it is able to check the timestamp of that particular file, and depending on where the file resides, it can run only that part of the build to include that new file within the make process. But to do that, we'll have to write the make file script accordingly. It doesn't happen straight away. So like in the linker script file, make also has its own syntax. It has its own way of writing the make, and learn of make here are the make basics. Again, you need to go through the make documentation, GNU make documentation, and you will get much more information about make. And there are some good books on make also which you can follow. So whatever we will learn here will be more than sufficient for you to write a basic make file and to manage your microcontroller projects using make. So let's look into the slides and take it from there, and we will see some demos and we will build a make file from rudimentary stage to an advanced stage, and thus we will understand the stages that the make goes through to compile and build something, and what we need to write to make that happen. So coming to make basics, make is a program to automate the conversion of source files into an executable. So we have been doing that manually anyway. So you saw that we did all of that manually. Now we are in the process of automating all of that. Well, at this point, some might ask, well, we could do the same if we automated the commands using some sort of scripting. So what makes make stand out? So make provides a streamlined way to lay out the dependencies between the various stages of compilation. If a few files change and a recompile is done using make checks the timestamps and only compiles the latest files changed after the last make. It also knows at this stage that the linking stage must be executed. GNU Make and other variants provide a language for describing the source code, intermediate file, and executables. Make can be considered central to the development process, where it can manage alternate configurations, implement reusable libraries for specifications, and parameterize processes with user-defined macros. So we can attribute a lot of speciality to make, which is required for the build process, which we cannot accomplish just by scripting alone. These are the commands that we have issued so far that we saw in that particular file. So these are the commands, and here are the commands we've been using to generate .o and .out files. Now we'll automate the process using make and evaluate the advantages of such a transformation. The rules that make uses is generally saved in a file called Makefile. However, this script can be named differently, and make needs to be used with a -f option if that's the case. So Makefile, within a folder, if you have a file named Makefile with a capital M, and within that folder, if you navigate into that folder and just type make will take this Makefile as the default Makefile. But if you have named the Makefile as something else, then you have to give make with a -f option and then the file name. So make will make that particular, similar to linking, where you have to give a -t and the build example.ld. If you don't give a -t, it will probably use some default linker. Similar logic goes here. Okay. Now come to make basics. Now all of make is dependent on this particular logic. Okay, that is, make has some prerequisites, any number of prerequisites it can have separated by space, and all these prerequisites will give rise to a target. That's it. Okay, so there are some prerequisites and there is a target. Now when you have and you have a series of statements like this, you have prerequisites and targets, and so on and so forth. Now each of these prerequisites again could be a target for some other line. Okay, so maybe this prerequisite is a target for another make statement that we have here. Prerequisite 2 could be a target for another statement. So what make actually does is that is how the make checks dependencies. It will go and check for these prerequisites as targets in other lines, and then it will check for the rules, and then it will come back here and then use this prerequisite to create this target. So this dependency checking is something that is exclusive to make. We will write a make file, but let us first go through this, whatever we have put here. Okay, so we have a target named build example.main. Okay. This is a part of the make script. We will see all of this in detail, but let us understand the concept here first, and let us understand what are the shortcomings of this particular approach, and then we can proceed from there. So say we don't put any prerequisites here. Okay. So here we don't put any prerequisites. We just name the target. So the target name need not be a file name. Okay. Target name is kept as a file name. It need not be a file name as well. So the target name is build example.main, suppose. Okay. And then this is the command that we put. So this is the first line of command that we have put. To just put the command, that's all. We have not done anything here. Okay. And then the second target name is again this. That is the core initialization STM32F411XE. And this is the command that we have put, which is the command straight away that we had been issuing manually in the terminal. And third is startup GCC, that is the target name, and this is the command that we have put. Okay. And this is the output. And here when we have put the output, we have named these three targets as the prerequisites. So because if you remember, we needed to create those object files previously and feed those object files into the linker stage. So this is the linking stage. So these three object files need to be fed into the linker. So we have named these three targets here as the prerequisites and then ran the linker command. Now these commands starts after the target name in the next line and it has to be tab separated. So it has to be tab separated from the margin, these statements. Okay, otherwise it will not work. And we give the linker command straight away as we do. And then there's another one, which is the creation of the binary. So it's the obj copy command that we have, and this one's prerequisite is the output here. So this is how it goes. So if you ask make to create the binary here, that is build example binary. See, if you do make build example binary here, it comes and sees the target here. Once it sees the target, it checks for the prerequisite. It says sees build example output as a prerequisite. It looks for the prerequisite as the target in the other parts of make. It finds the prerequisite as the target. Okay, and then for that target again, it checks that it sees that there are three prerequisites. It goes to those targets again and then runs the commands, gets the prerequisites done, and then it creates the output. Then the output comes here, and at the end the binary is created. So you see how make. So if you change the name here or here and it is not able to find these prerequisites in the targets anywhere, make process is going to fail. Okay, so that is how make checks for the dependencies. Build example binary, make will say build example output. If this is not there, suppose it's some different name, it fails at this stage only. So make creates a dependency tree and it parses the tree and it takes care of the process. Now, what is the drawback? I mean, what's the disadvantage of this particular make script? The drawback is, since these are not file, it takes these as target and source names. Make has no issues in taking these as names of sources and targets. Okay, but as you can see, these are not file names. Okay, these are just source and target. These are just some names. Now the problem with this is, make will suppose now after the make process you update core initialization STM32F411XE, this file. Okay, you update this C file here. Okay, when you run make will not rerun the process here because it is not able to associate this with a file name. So it will not know that this particular file has been changed since the last make process. So the prerequisites have to be at least we know that the prerequisites have to be file names. Okay, that is, make has nowhere to check the version of, because these files are not created. We build example main.c is available. We have all these as .o files. So this is build example main.o. Suppose the target is build example main.o, but we given the target name as build example main. It will accept this as a target name, but then it does not have a file to check it against. So it's not going to know what needs to be done. Okay, probably it will run the whole make process again, because it doesn't find anything, so it thinks that it's a fresh make process. If it finds the binary file, probably it will say nothing to be done, and so on. So we will write this make file, and we will change the files here and there, and we will see how it behaves. So as we see, every time we run make, the script does not seem to keep track of the timestamps of the source files. Okay, so that's one disadvantage of writing the make like this. So the first rule, or the default rule, consists of three parts, as we discussed: the target, prerequisites, and commands. The commands have to fall in the next line and must be separated by a tab. Since the target of one rule can be referenced as a prerequisite for another rule, the set of targets and prerequisites form a chain of graph of dependencies, short for dependency graph. And we talked about that. So the graph that you see, this graph is a dependency graph. So it might look like this. So build, say, okay, let's write this. Let's draw the graph. It may not be storing it in this way, but nevertheless, let's see how the graph may look like. Okay, so suppose we have build example binary, okay, which is dependent on build example output. So you have build example binary here. Okay, which is dependent on the build example output. Okay, now build example output is dependent on, again, three targets: build example main, build example core initialization, and then we have startup GCC. So the dependency tree may look like this: build example binary, build example output, and then it again depends on these three values. That is that, and this need not be linear. If you write something here also, as it encounters. So if you write the startup GCC rule after the build example output, it can actually search for the file and come here and then add the startup gcc.c to this node actually. So make is intelligent enough to do that. Okay, so this is the dependency tree that make creates to resolve the dependencies. So this is a major advantage of make. But of course, as we said, it is not taking care of the timestamps of the source files if we write the make file like this. Now what we do is we change it one more step. Everything remains the same, but instead but only thing is we change the names of the targets here. Now instead of just the name of the targets, we actually name it, we give the file names here of the output files. For example, like build example, instead of build example, we give build example.out, startup gcc.o, core initialization stm32xe.o, build example main.o. Okay, so here at least make now has timestamps of the targets. Okay, but make is still not keeping track of the source files, so the prerequisites might be needed after all. Okay, because source files still don't have the names here. So we have also the prerequisites, we have put the .o files as the prerequisites here. That is all fine. Okay, but then remember one thing: the .o will only change if the sources change. So make might be taking into account the version, or taking into account the timestamp of these files, but then we are still not accomplishing our goal. Okay, so the source files also have to be mentioned here for make to really do a version check of the source file. And since the source files are not there, the prerequisite source files as prerequisites are not there, make will find it make will not find them and it will not do any version check. So the third option is to have the names of the source files put in like this. Okay, so this is the target, this is the prerequisite, this is the target, this is the prerequisite. Of course, this .c file is compiled into .o, this .c file is compiled into .o, and here you put the prerequisites and so on. In this case, you will see that if you change any source file here, make is going to rerun that particular step, and only that particular step wherever the source file has changed, and then make will run and create the binary file again. Okay, so I hope it is clear till here. So we are evolving the make file step by step. Previously we didn't have any prerequisites except for a few. Then we added the target file names. Now we have added the source file names. So make will take care of the source versions as well. So far, whatever we have seen in make is just enough, sufficient enough to write our basic make file and for our code. But that's not the objective here. We will learn some more advanced make file and make tricks to make our job more easy. So for that, the first thing is we need to know about the make. Just have some information about the make rules. So a rule does not have to be defined all at once. Each time make sees a target, it adds the target and prerequisites to the dependency graph. We will work with only explicit rules for our requirements. So there are rules are of type explicit, pattern, and implicit. And then pattern again has static and regular rules. Implicit has suffix, and then implicit also maps to pattern. So we will not look at this side. We will only work with explicit rules, which should be sufficient for our requirement. But then we need to know the further tips and tricks that we can apply with make. Just like we had variables in linkers, make also has variables. And there are two types of make variables, which are called simply expanded and recursively expanded. Simply expanded is denoted by equal to and a colon. That variable has a right-hand side, are expanded, and the resulting text is saved as the value of the variable. So when you assign such a variable, the variable value is assigned during when you write this a variable equal to colon, instead of this statement, the value of the variable is saved there in the make process itself. Okay. Now, recursively expanded variables are given by an equal to. Okay, it is not equal to colon, but just an equal to, and it has a right hand side simply slugged up by the make and stores as the value of the variable without evaluating it or expanding it in any way. Instead, the expansion is performed when the variable is used. So here, when you declare the variable, at that time itself make assigns the value of the variable. Here, when you declare the variable, it just accepts the variable and uses the value when it is using the variable, not before that. Okay. We will be using recursively expanded variables in our application, and the variables are accessed with a $sign like so, like this. So you can declare variables like this. So cc equal to gcc, suppose. So cc is the variable name, and the right hand side is actually the variable. Now this one is going to be when you use cc in the script itself. When you are using cc in the rule, that is when this gcc is going to be substituted there. It is not going to be substituted at this stage. Similar to this. And for example, so if you want to use these variables again, you have to put a $, and thus you have to $build prefix, $cc, and so on. So this one actually means build command equal to build prefix is arm none eabi, and $cc is gcc. So build command would mean goes like this. So this is gcc. So dollar, so if you have to access the variable, so dollar, this dollar build prefix is arm none EABI, and then $cc, just since you have a dash here, it becomes arm none EABI, and this string is just added as GCC here. So you can add the strings like that. Okay, dollar and dollar. So eventually you get a string like this. Now if you have to access the build command again, you have to give a dollar build command. So it should be dollar. Okay, to access the build command from your rule. Okay, so this is something that you have to do. So it's more or less straightforward. We are using recursively expanded variables, but henceforth we just call them variables. We don't need to bother much about this. Now, automatic variables is another important feature of the Makefile. That is, let's assume that you have the target and you have the prerequisite. So this is the prerequisite and this is the target, like we saw previously. Now you might have a lot of prerequisites here. So the prerequisites can go to any number of files. Okay, and we'll also see that we need not write the prerequisites here, all of them. We might have the prerequisites mentioned as variables somewhere else and just give a dollar and the list of the prerequisites here. Okay, whatever the case, suppose you are writing a none ABI GCC and you are putting all of these commands. So we have been putting all of these commands, but then C flags, and we have declared C flags as something, whatever it is, we'll see that later. So this is some variable C flags, and then the left hand side, the entire left hand side here is represented by $@. That is, the target is represented by $@, and the prerequisite side is represented by $caret. Okay, so now what this means is, if you even have multiple files here, say core initialization stm32f411xe.c and main.c, whatever it is, if you have a long string of file names on the right hand side, the whole thing can be just represented as $caret. That's all. You don't need to call these files over and over again. So it's kind of just like parameterizing these file names here, and the left hand side similarly is represented by $@. So if you change the file names here, and again we will see that this can also be parameterized, and we will create some variables and have this file list mentioned there, and we'll just reference it here. So changing it in one place will have an effect on multiple rules, right? So let's anyway go through the slides. So automatic variables are special variables set by Make and provide access to members of targets and prerequisites. Automatic variables save the effort of typing the target and prerequisites repeatedly, especially in the commands. Sorry about this typo, especially it should be S, not X. Sorry about that. So there are 6 types of basic automatic variables, out of which we will use 2 here, namely $@ and $caret. $@ represents the file name representing the target, and $caret all the prerequisites separated by spaces. This list has duplicate file names removed. So going forward, we have 2 path variables that are used in Makefile, which one is called vpath with all caps, and another one is vpath with all small. And these two have subtly different meanings. One is, so in the traditional source tree layout, the header files are placed in an include directory, and the source is placed in an src directory, as we have done. In such cases, the prerequisites and the targets will need to refer to files in different directories in the tree. Okay, so as we discussed, it has to know where the files are residing. Now, vpath and vpath consists of a list of directories to search for the files make needs. Okay, and vpath is for the files make needs, and small vpath is a more specific search, and hence it's quicker than vpath, as vpath helps to search only a particular type of file in the list of directories. So we'll see that. So if you declare capital vpath, that is vpath all caps, then it will search for one file. It will search for that particular file in through all directories. So if you say you're searching for a header file, it will search in the source directory also, irrespective of whether it's a header file or not, or a source file. It will search in the header and it will traverse the whole tree. vpath is more specific. So in vpath, if you are looking for a .c file, it will only search for those folders in the tree which has .c files. It will not go into other folders, say include folders, to look for a .c file. So vpath is much quicker. vpath, on the other hand, treats all directories in the same way as searches uniformly, as we discussed. Only targets and prerequisites have access to vpath and vpath. Now, this is very important. So you have targets and prerequisites, as we saw, and they only have access to vpath and vpath. Nothing else has an access to vpath. Automatic variables follow vpath or vpath as they represent prerequisites and targets. So, for example, vpath is declared this way: source directory, include directory. So you have a list of directories, and if you are searching for anything, so say source.c file, it will go through all the whole directory tree and it will search for your file. vpath is specific. So here, as you can see, we can declare vpath %c look into the source directory, vpath %h look into include directory. So here the search is more specific. If you're searching for one type of file, say a header file, vpath searches only in the particular directory it's instructed to. So we will be using small vpath for our application. Though we have in the Makefile, we have mentioned vpath somewhere. We may check with vpath saying to see if it works, but generally we are going to use small vpath. Now, there is something called as a phony target. Now, we'll need a little bit of explanation of how the targets are handled. Now, whenever you have a target, and we have seen that if the targets are up to date, that is since the last make, if the target has not changed, make says nothing is there to be done. So basically, make will say that I have run the make and none of the files have changed since my last run, so I'm not going to do anything. Now, phony is it's a false target, and what basically happens is, if you name a target as all, suppose you can name the target as anything, right? So if you say phony all, and then say suppose you have the output binary, so you would have seen make all commands given in your projects, or you would be seeing make all in many places when you have to build your project. So generally what happens is, again, this dependency starts from here, and we'll see that in the demos. So it starts from all, but then this all, whatever target we have, suppose we have a file name called all in the directory. Suppose we said previously, when we in the initial stages of our of the Makefile slides, we said that the targets, so if the targets are not file names, it will not be able to discern between the versions of the particular files. Now, what happens here is, if we declare a target as a phony, even if all exists as a file, say suppose a file name exists as all, suppose, even if it exists, phony targets will disregard this particular file and it will run the make anyway. So it will not say that this all has changed since the last has not changed since the last make. I'll just keep quiet and I don't want to run it. It's not going to happen. So phony is going to take care of that. So for targets that you absolutely need to run every time, it is better to have a phony target. For example, clean. Clean is when we have to clean up the output file. Suppose we have an rmrf command given here, which removes the files in the Linux systems. So you say you give a clean and make it phony. So even if there is a clean file named clean here, it will disregard that file and run this anyway. Yes, so that is the job of the. But then suppose it is this output binary depends on other prerequisites and all that, and if they have file names, even if you do a make all, it will get into the make all and it will try to go parse the tree, that is the dependency tree, and if it sees that these files have not changed, it will still tell you that nothing is there to be made, but at least it will go into the make process and do that dependency check. That's phony target. So targets that do not represent files are called phony targets. Generally, if a file exists with the same name as the target and the target does not have prerequisites to remind the target that it's out of date, the rule would never be executed, as the target will always be considered updated. Okay, so in that case, phony always makes the target look out of date even if the file exists with the same target name. Phony targets may be needed in special cases as shown below. Empty targets are targets without phony keyword. They are used for certain special purposes besides creating executable files. Okay, so there are something called as empty targets as well.